All right, today we're going to get to know the one element that basically makes everything, well, everything. We are talking about the universe's ultimate superhero, carbon.
Yep, that's right. From the breakfast you ate this morning to the actual DNA inside your cells, carbon is the absolute star of the show. So how in the world does it do it? What's the secret sauce that makes this one element the foundation for all life? Well, let's start with something that might surprise you. You'd think that something so important would be everywhere, right? Nope. Carbon is actually super rare. I mean, look at these numbers. The Earth's crust is only 0.02% carbon. The atmosphere? Just 0.03%. It is the ultimate chemical underdog. But, and this is a big but, here's where it gets crazy. Even though it's so rare, carbon forms millions of different compounds. That is literally more than all the other elements on the periodic table combined. So how does this quiet little underdog become such a powerful superhero?
That's exactly our mission for today. First, we're going to dive into carbon's secret origin story. Then, we'll check out its incredible superpowers. After that, we'll meet its team of atomic buddies, and we'll even solve some big questions you might see in your textbook. So let's get into it.
Okay, first up, the origin story. You know, every good hero has one, and carbon's is all about its amazing ability to make friends. It's not about stealing electrons or taking them from other elements. No. Carbon's secret is all about sharing. And this special kind of bond has a name. It's called a covalent bond. Instead of one atom just handing over an electron to another, two atoms decide to share a pair of electrons between them. You can totally think of it like they're locked together with the world's strongest friendship bracelet. It makes the whole molecule super stable and happy. And here's that sharing power in action. What you're looking at is methane. The carbon atom is right in the middle, and it's sharing its four outer electrons, we call those valence electrons, with four different hydrogen atoms. By doing this, every single atom in the group gets to feel like it has a full outer shell of electrons, which is what makes this little molecule so incredibly stable.
Now, this whole sharing superpower leads to some pretty specific traits. Compounds that are built with these covalent bonds, they tend to have low melting points and low boiling points, and they're usually not very good at conducting electricity. So why is that? Well, while the friendship bracelets inside each molecule are super strong, the forces that hold one molecule next to another are actually kind of weak. That makes them easy to pull apart with a little bit of heat. But listen, sharing is just the beginning. It's just level 1. Now, we're going to unlock the two secret properties that really make carbon the most flexible, adaptable hero in the entire elemental universe. Okay, superpower number 1, tetravalency. Tetra just means 4. Carbon has 4 of those valence electrons we talked about, which means it can form 4 covalent bonds at the same time. It's like having 4 hands to shake hands with all its neighbors. Superpower number 2 is catenation. This is carbon's really unique talent for linking up with itself over and over again to form these long, stable chains, crazy branches, and even cool-looking rings. And when you combine those two awesome powers, you get something truly amazing called allotropes. Allotropes are just different versions of the exact same element. The best way to think about it is like a superhero having different suits for different missions. Same hero inside, but a totally different look and completely different abilities on the outside.
I mean, this is the perfect example. Diamond and graphite are both 100% pure carbon. That's it. But in a diamond, all the carbon atoms are locked into this super strong 3D grid, which makes it the hardest thing we know. In graphite, the atoms are arranged in these flat sheets that can just slide right past each other. That's why it's so soft and slippery, and why it's perfect for the lead in your pencil.
So here's the crucial takeaway. The arrangement of the atoms is everything. It's the same element, but just changing how you build it, well, it changes everything about it. And that is the key to carbon's unbelievable versatility.
But of course, carbon doesn't just work alone. It's a total team player. Because it can form those 4 bonds, it's super friendly, and it can assemble this amazing team with other elements to build the molecules that make up life itself.
The most basic members of carbon's crew are called the hydrocarbons. That's just a fancy word for compounds made of only carbon and hydrogen, and we sort them by the type of bonds they have. You've got alkanes, which have all single bonds, alkenes, which have at least one double bond, and alkynes, which have at least one triple bond. It's really that simple.
But things get even more exciting when other elements, we call them heteroatoms, join the team. When something like oxygen or chlorine comes along and replaces a hydrogen, it creates something called a functional group. And this new group gives the entire molecule a totally new identity and brand new abilities, almost like a special power-up in a video game.
So you're probably wondering, how on earth do we name millions of different compounds? Well, we use a kind of secret code called nomenclature. Let's crack it right now. Step 1. You count the number of carbon atoms in the longest chain. That gives you the first part of the name. For example, 3 carbons gives you the prefix prop. Step 2. You find that functional group, the power-up. An alcohol group, for instance, gets the ending -ol. So put them together, what do you get? Propanol. See, you've got this. All right, theory time is officially over. Now that we know the rules of the game, let's actually put our knowledge to the test. We're going to solve a couple of common questions that you might even see on an exam. First challenge, carbon dioxide or CO2. We know the formula, 1 carbon, 2 oxygens. But the question is, how do they all share their electrons to get stable? Let's figure it out together.
Okay, let's break this down. Carbon starts out with 4 outer electrons, but it wants 8. Each oxygen starts with 6, and it also wants to get to 8. So what's the solution? Well, the only way to make everyone happy is for the carbon atom to share 2 of its electrons with 1 oxygen, and the other 2 with the second oxygen. This creates 2 really stable double bonds, and boom, you've got the electron dot structure for CO2. Everyone wins. All right, you ready for a trickier one? A molecule made of 8 sulfur atoms, S8. And the question gives us a huge hint. We know they form a ring. So how does that work? Well, if you look at the periodic table, sulfur is in the same family as oxygen. That means it also has 6 valence electrons, and it really wants to form 2 bonds to feel stable. So just picture 8 sulfur atoms holding hands in a long line. The atom at the very front of the line can then just turn around and hold hands with the atom at the very back. The chain basically bites its own tail, and it forms this stable, crown-shaped ring where every single atom gets the 2 bonds it needs. Pretty cool, right? So after all that, from friendship bracelets to superhero suits and biting chains, what's the big takeaway here? It's really this. Carbon's 2 simple powers, the power to form 4 bonds and the power to link up with itself, are the secret recipe for creating the almost endless complexity we see all around us. It's how one simple underdog element ends up building, well, you. And that really just leaves us with one final thought to chew on. We know carbon can be arranged to be incredibly soft or unbelievably hard. It builds our bodies, it fuels our cities. So the real question is, what's next? What new materials, what new medicines, what new technologies are just sitting out there, waiting for us to discover them, all built from this one amazing, versatile superhero element? Thanks for joining me.